Okay, section 6.5, vector vectors in R2 and R3. So real number, two space and three space is what that stands for. So that's just the Cartesian plane. We're going to define three space though, and that incorporates the z components of x, y, z, the depth component, and three spaces, your space, the space we live in, right? We were three-dimensional worlds, so that's really not a big new concept, but we see it through mathematical approaches, and we're going to also just touch on real quickly 2D space vector representation. So here you go. This is going to be really quick and simple and right to the point. So 2D vectors can start at the tail, at the origin, a Cartesian system. We talk about the Cartesian system. The vectors, remember, can start really anywhere and follow that same direction. A vector representation on the Cartesian plane has really strong ties to slope and our understanding and idea about slope, except we give the vector representation as we're used to giving it in the Cartesian plane, and that's xy component. Okay, so express each of these following vectors with scalar components or coordinates here. Okay, so the first one, vector A, it starts at, okay, here's our tail, it starts at 0, goes 2 units back along the x direction, and then it goes 3 units up along the y direction. That's how we say that. Okay, for vector B, okay, we've got starting at the origin and ending up at that point there, and I could find that point, okay, by just identifying it. So it would be 1, 2, 3, 4. Okay, so the end or the head of the vector would be the point 4, -1, and that's exactly how I represent that as a vector. Okay, 4, -1. Not a real challenge or not a real problem, I think, at this stage. Just to understand the difference between, okay, that is an ordered pair, okay, or a point, that would be the point 4, -1, or the vector, okay, if I represent it with a vector, okay, it's the vector A starting, okay, at a point and then traveling, and then the origin, the start point can really be irrelevant, okay? Even if we drag that vector, okay, up to here, okay, my straight lines are not good. That should be a straight line. My vector B would still be, okay, from my starting point to my ending point. So it would still be 4 over, okay, +4, okay, or 4 in the right direction, and then 1 unit down, and that would still be that same vector. So the origin or the starting point is really irrelevant. It's all about the direction of the vector. Okay, so vector components in two-dimensional, as a two-dimensional vector here. So we can talk about, okay, the y component as following along in the j direction, okay, and we talked about I and j, and those being the unit vector for the x-axis, so it's I, or I hat, and j, okay, as being the unit vector for the j-axis. So what this looks like, okay, in vector component form, okay, it's the, okay, this representation right here, okay, so I can represent vector as the order pair 3 and 2, but I can also represent the vector, the resulting vector v, okay, as 3 times I, okay, and that's just, this is 3 times I. Let me just get back to my pen tool here. That's 3 times I, and then plus 2 times j. Okay, and there's my I, and there's my j. So this one was 3, 1, 2, 3, and then 1, 2. Okay, so that was 3i plus, okay, that's, okay, tail to head, and then plus 2j, and that's the vector in red here. Okay, so anytime I have a position vector, okay, I can represent that with a Cartesian point in a sense, or components, and I can also represent it as a string or a combination of two vectors with scalar multiplied by the unit vector here. So we'll go through this a couple of times here as this example. Okay, so before I do some of these combination of vectors, I'm going to just review magnitude of vectors. How do I find the magnitude of a vector if it's in component form. That's relatively easy to do. I use the notation and I just squared plus I should have used brackets. And that would work out to be 16 plus 9 square root 25 or 5. That's Pythagorean triple that we know. Okay, the triangle 4 the component 4 negative 3. Okay, so 4 negative 3 is down here. Okay, and that's, you'd recognize that as a Pythagorean triple. That's how we do vector notation. Okay, so these, I've referred to these as the standard unit vector. I is the vector 1, 0, and j is the vector 0, 1. Okay, lots of definitions and just some ideas here before we get started with vector. And displacement vector in 2D, I talked about this as well too. So my displacement vector, this example here is the displacement vector. Explains the pathway that I go from M, starting at M, all the way to ending up at N. So the M is the point 2, negative 1, and N is the point 0, 2. My displacement vector, Mn, is found so my displacement vector would be the vector negative 2, positive 3, and that's represented here, here, or with component vectors. Now, to find that mathematically is up here, this formula. So Mn, many students like to see the calculation. So read this as I'm starting at M and I'm going to N. So I want to take my point N, 0, 2, and subtract M from it as components. So I subtract the x's 0, take away 2, and then I subtract the y's 2, take away negative 1. And that would be negative 2, positive 3. And I'm just going to clean that up in case people are really paying attention to this. And that would be negative 1, and close my bracket here. So that's really, going backwards 2 and up 3. And that's the pathway I'd go if I was a particle following along this displacement vector starting at M, moving along all the way to N. That's the pathway I'd go and be similar to going 2 units backwards and then 3 units up. And again, we really see the connection here with slope. All right, scalar components of 3-dimensional vectors. All right, here we go. So here's the third z-axis or z component when we talk about 3D vectors. Now this is represented like this, real number system, 3 space, and that's referred to as the 3 space with vectors in a sense. Now they're also called vector triples, and they incorporate these 3 dimensions. Now think of x, y as the original Cartesian plane that you know, and z just gives some depth to it. Standard unit vectors would follow that our unit vectors I have to include the third component now. So it's 1, 0, 0. J would be 0, 1, 0, and K, following our alphabetic way to look at things, would be 0, 0, 1. So here's the Cartesian plane, and using the third component, how do I convert this one to component form? Well, that's really just easy. I focus on, and really just a kind of a definition lesson here, housekeeping lesson, so we can establish some grounds here. So I can represent my vector like that as well too. Okay, so the vector 4, 0, 3, the vector components, I could have 4i. Now you'll see now you may also start to see, I wouldn't normally write that. Oops, that's okay if I can't drop that originally. Okay, now you may also see instances where it's okay. The hat symbol here, the hat symbol just represents a unit vector. Okay, pretty straightforward, I think. I don't think this is going to be a big challenge for a lot of students here. Okay, so show the algebraic position of vector OP where P is 3, -2, and 4. So algebraically, we want to show the vector. Here's my origin. Okay, and I want to show the vector 3. So that's the x component. X is out here, so I'm going 3 units up. Okay, make careful note of how our Cartesian is playing with the third component now is oriented. Okay, so my vector, my resulting vector P, okay, or OP in this case, because O is the origin, okay, ends up at 3 units in the x direction, okay, -2 units in the y direction, so that's backwards, and then 4 units up, 4 units in the z direction. So the three-dimensional diagram doesn't really do it a whole lot of justice. Part of this unit is going to be to find an online 3D plotter that will really make these visuals a whole lot better. That's always been an ongoing challenge for us, but that's the idea. If we have this, okay, we want to talk about 3 units. 3 units, okay, so that would be x component, so that's 3 units right. That would be 2 units, that's the y component, so it would be 2 units down because of the negative, that's because of the positive, and then 4 units up, and that's because of the positive 4 here. All right, displacement vector with 3 components. Hey, that's not a problem. Again, just sort of reviewing the definition. When we have a third component, we just have to write the vector as a third component. So what's the displacement vector PQ for this example here? Well, remember I'm starting at P and I'm ending up at Q. Okay, so I have to take my second vector and subtract my original. Okay, so my x component is -2, take away 1. My y component is 3, take away -2. And my z component is -4, take away 3. Okay, so my x component is right here. That's -3. My y component is 3, -2. So that's 3 plus 2 is 5. And then I've got a -7. So think about this in a second here, okay? So I'm starting at P and ending up at Q. Okay, so if I start at 1 and end up at -2, I'm going backwards 3 units. Okay, if I start at -2 and go to 3, I'm traveling forwards 5 units. And if I start at 3 and end at -4, I'm going backwards -7 units. And that's really how we do that. Really learn how to do this though. I mean, there's going to be some homework questions where we have to do that. So make sure we know how to really take that and talk about starting at P, ending up at Q. So taking my second point, my Q point, and subtracting my first point to it. And you're going to see, the more you do this and understand this, you're going to see that this is really just a slope calculation, except of course we represent it as a vector. That's it, homework questions. I've got a diagram here for a Cartesian plane, and we'll get right to it. Thanks very much. That was a short one.